Hello again. In this video, we're going to go over an example where we use Newton's method to approximate the x-intercepts for a function. Okay, so the example we're going to look at is the one down here where f of x is equal to x cubed minus 5x plus 1. Now the graph of that function looks like this, and notice that it does have three x-intercepts here. And we're going to try to approximate each of those x-intercepts using Newton's method. Now remember, the first step in Newton's method is to come up with an educated guess for the x-intercept that you're trying to approximate. So let's suppose you're trying to approximate this x-intercept here, and your initial guess for it is 4. Now we always label the initial guess as x sub 0. And then kind of a reminder of how Newton's method works is then you take your initial guess and you plug it into the function to get the ordered pair for that particular point. So in this case, you would plug 4 in to the function and find the corresponding y value, f of 4. Of course, that point is going to be this ordered pair here. And then you draw a tangent line at that point, and you see where that tangent line intersects the x-axis at. And wherever it intercepts the x-axis at, you label that as x sub 1. And then you plug x sub 1 into the function and find the ordered pair for x sub 1. So in this case, it would be x sub 1 comma f of x sub 1. And that would be this point right here. And then you go through the same process. You draw a tangent line at that particular point and see where it intercepts the x-axis at, and then you label that point as x sub 2. And now you can just continue to do this. And notice as you do this, you're going to get a sequence of numbers that begin to approach the x-intercept. And then at some point, we can stop the process, and whatever number we're at will be our approximation for the x-intercept. Okay, now remember, the last video I derived this little formula that we can use to find the numbers in that sequence, x sub 0, x sub 1, x sub 2, x sub 3, and so on. So in this case, x sub n is the previous number in the sequence, and then x sub n plus 1 would be the next number in the sequence. So as long as you know the previous number in the sequence, x sub n, then you can find the next number in the sequence, x sub n plus 1, using this formula. Okay, so let's find that formula for this particular function. Okay, so notice in this formula, we do need to find the derivative of this function, which gives us 3x squared minus 5. And then notice we evaluate that at x sub n. And so that's just going to give us 3x sub n squared minus 5. Okay, so we have x sub n minus f evaluated at x sub n, which means we just plug in x sub n for both of these x's here. That's our function. That's going to give us x sub n cubed minus 5x sub n plus 1. And all over f prime evaluated x sub n, which is this. Okay, so if we know x sub n, then we can find x sub n plus 1 using this formula. Now, it may be nice to have a common denominator so we can simplify this. So I'm going to go ahead and multiply x sub n by 3x sub n squared minus 5 divided by itself. Now, notice that's equal to 1. And the reason I'm doing that is because then we'll have this common denominator here and here. Okay, so it's perfectly legitimate to multiply by 1 because it doesn't change the value of it. But now we're going to have the same denominator. That way we can now subtract the tops. Okay, but before we do that, let's distribute this x sub n, and we get 3x sub n cubed minus 5 times x sub n. Okay, and then we're going to have to subtract this off, and so we're going to get a minus x sub n cubed then a plus 5x sub n, and then minus 1. Okay, and that's going to be all over the common denominator, which is 3x sub n squared minus 5. Okay, and then we just can combine like terms. So 3x sub n cubed minus x sub n cubed is just 2x sub n cubed. And then the minus 5x sub n and the plus 5x sub n are going to cancel out. That's going to leave us with this minus 1. Okay, all over that common denominator. Okay, so now we have a nice little formula that will allow us to find the next term in that sequence in Newton's method, if we know the previous term, x sub n. Okay, so let's apply this to our educated guesses that we're going to make for each of the x-intercepts that we're trying to approximate. Okay, so we have 3 x-intercepts here that we're going to try to approximate. And let's start with approximating this one here. Okay, so let's say our initial guess for this one is going to be negative 3. Okay, and of course we label that as x sub 0. And what you do is you plug in x sub 0 into that little formula. So here's our formula for x sub n plus 1. And then we plug x sub 0 in for the x sub n, because n is 0 in this case. And that's going to give us x1, x sub 1. Okay, and then our guess for x sub 0 is negative 3, so you can see you're plugging a negative 3 in for those. And then you just plug that into your calculator and you get negative 2.5. And so that's x sub 1. But then to find x sub 2, you take x sub 1 and you plug it in to this formula, right, which is basically plugging x sub 1 in right here. And that's going to give you x sub 2, right, because n is 1 here, so that n plus 1 is going to be x sub 2. Okay, and then x sub 1 we found to be negative 2.5, so you can plug that into here, and just plug this into your calculator, and you get this approximate number here. Okay, so that's kind of how this works. And so if you look at this little table, it summarizes what's going to happen if you continue to do this. So x sub 0, we guessed negative 3, and then x sub 1, we get negative 2.5, and then x sub 2 gives us this number. And if you continue to do this, you're going to get these numbers out. So x sub 3, x sub 4, x sub 5, x sub 6, x sub 7. So when do we stop, right? It's a good question, is when do we stop, right? Because this can continue on forever. So a good rule of thumb is you stop at however many decimal places you want to be accurate to once you get a repetition in that number of decimals. So for example, if I wanted to be accurate to within, say, 3 decimals, I would continue to do this until I get a repetition in those 3 decimals. So 330 and then 330, that's when it begins to repeat. Okay, and then I could stop and say, well, this is accurate to 3 decimal places. So it just depends on how accurate you want to be as to when you stop. If I wanted to be accurate to 1, 2, 3, 4, 5, 6 decimal places, then I would have to wait until this repeats for those 6 decimals. And that happens right here. So then I could stop and say I'm accurate to 6 decimal places with this estimate or this approximation. Okay, so I'll leave it to you to fill in the rest of this if you're curious. But then to find the next x-intercept, which is right here, our initial guess might be 1, and so that's going to be our x sub 0 right here. And then you would just plug that into the formula, and then you would get negative 0.5 out. And that would be your x sub 1. And then you would plug that into the formula to get x sub 2, and that'd give you this number. And you just continue to do this, and stopping whenever you reach the level of accuracy that you desire in the number of decimals, and having them repeat. Okay, and then the last one, we decided to use 4 to try to approximate this one. So you would start off with x sub 0 is equal to 4, plug that into this little formula, and then that would give you x sub 1, and then plug x sub 1 into the formula to get x sub 2. And again, you would continue to do this until you reach the level of accuracy that you desire. So again, if you wanted this to be accurate to 6 decimal places, that would repeat once you get to x sub 7, right? It would repeat here and then here in the first 6 decimal places. Okay, so this would be accurate to 6 decimal places. Okay, so that's how we use Newton's method to approximate x-intercepts for functions. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.